So for this module, we are scheduled to cover linear approximation, section 4.1 from the book. And so the general question here is how do small changes in x affect a function f? Sorry about that. How do they affect it? Well, from the point of view of general functions, this question is almost impossible to answer. But if we assume that the function has some regularity, then we can give pretty good estimates. So if you remember, I mean, if this is something more of a philosophical insight, but I mean, this actually can be made quantifiable. So differentiable functions. So this is our guiding principle. Are functions that can be approximated by linear functions. And yeah, how do we know that? I mean, going back to the picture from the beginning of the course. So we have any function like this one. Say, the thing is, at any point, like this one, x0, we can draw a tangent line. The existence of this line implies that, well, this is f. This line here, the tangent line, is a good approximation of f. And that's basically what it means for f to be differentiable. So if at the limit of the slopes of secant lines approach a value, it means that you can define the tangent line. The fact that you can define a tangent line means that the function can be approximated by a linear function. Okay, so if we zoom in at the point x0, what we'll see is something like that. And if we zoom in even more, you'll see that the function f looks almost at this scale, looks more and more like L of x, and that's what led us to, well, the definition of the slope of the tangent line as the limit. I always remind you to keep in mind the definition of derivative. So this is f prime at x. Right, so if you go back to the drawing, the original drawing, so this is the slope of the secant line, and it is approaching a limit because this function is not oscillating wildly, but it is getting closer and closer to a line here. I mean, the slopes are getting closer and closer to a line L. So that means that the slopes are approaching the slope of that line L. And that's a linear function. So an example of a function that's not differentiable, you can see something like this. I mean, a kind of a canonical example of function that is continuous, but it's not differentiable, is the absolute value of x. We already already used this example in the past. So let me just do it like that, and then over here, and this is the f of x is the absolute value of x. And this cannot be approximated by a linear function. So which one? So if you try to use, say, this line over here, oh, let me just use actually something else. Use a color. This line over here is not a good approximation. See, for points arbitrarily close to 0, here this is not providing a good approximation. It's a better approximation on this side, right? If instead you say, oh yeah, but that's because you are not choosing this straight line. So you only have basically two options here. It's either this line or this line. But you cannot have both at the same time. So either you approximate perfectly f of x by a linear function on one side or on the other side, but you cannot do it at both. Okay, so that means that the two options in yellow are perfect and linear. Linear approximations of f. But only on one side of x equals 0. On the other hand, any other line, such as the blue line, will not be a good approximation. Mention neither. Either side. Okay, so and that's because the function cannot, there's no function that will approximate, there's no linear function that will approximate f at 0. Any linear function that will approximate it very well. So that's why when you have sharp corners, then the function is not differentiable. Okay, so you have to see something. But in any situation where the function is kind of rounded, you see, of course, on this side, the slopes so on one side, here the slopes are a little bit smaller, and on the other side, the slopes are a little bit bigger, but they're actually very close to the slope at the point. So that's the limiting point. So that's usually the case when you have functions that are not only differentiable, well, the derivative is continuous. Since most of the functions we treat in Calc1, like polynomials and exponentials, are many times differentiable. One of the things that we discuss plenty of times is that differentiability implies continuity. And so if they are differentiable, if they are differentiable infinitely many times, then that means that the derivative is itself continuous because it's differentiable. So most of the situations we encounter, this is the picture we should have in mind. So the slope is changing very very smoothly, and so So, but all this discussion is to say that if we have a if a function is differentiable at a point x0, by the very definition of differentiability, this implies that the change in f must be approximately equal to the value of prime at a, or the point x0, times delta x. Why? Because the limit, remember the limit here that we're considering when defining f prime is the limit of delta f divided by delta x. Delta x goes to 0. I mean, this quotient here is the on top. I mean, this difference here is the difference in the values of f, or delta f, and h is the difference between x plus h and x. So that's delta. That's our delta x. So just because that limit exists, it means that this approximate the f prime, well, delta x gets closer and closer to 0. Delta f divided by delta x is approximately equal to f prime of x0. And that means that this means that this means that the function, the linear function L of x, defined by L of x is equal to f prime n at x0, the point x0, times x minus x0 plus f, the value of f at x0, approximates f really well for values of x really close to x0. Okay, let's go back to our drawing. Let's go back to our drawing, and we see that here let me just move a little bit bigger, perhaps. Okay, so this is f of x. This is the point, say, x0. And this height here is exactly f of x0. That's how, that is the value of the function at that point. And let's look at this line here. This line has a slope. This is L, and it has slope f prime at x0. Now this is the slope of the tangent line, and it passes through f of x0. We've used this in we already asked you to find the equation of the tangent line many times, and the equation of the tangent line. So the equation of the tangent line, which is L, is y minus the value at that particular point, which is f of x0, and that is equal to the slope. This is slope form, point slope form of a linear function, prime of x naught times x minus x naught. So therefore, well, actually y here is the value predicted by L of x. So if you move f of x naught to the other side, you get exactly the equation for the tangent line. And this is what we're saying. So, and you see that the tangent line, when you're really close to x naught, the linear function L takes values that are really close to the actual value of f. But as you move away from the point x naught, you consider a point that is far apart, you see that the gap between the actual value of f and the value predicted by L gets bigger. I mean, there's no reason why something that behaves locally like a linear function L will look like the same linear function elsewhere. Okay, so that's the point of this first part. So the introduction is just to say why we are why we can approximate things and we'll use them. We'll use the linear function to approximate the actual function f. Any function f that is differentiable and for which we know certain things about its behavior locally. So here, in order to be able to apply this for particular problems, there are two things that we need to know. Of course, the thing is, when we're dealing with the complicated functions, such as sine, cosine, we don't know. I mean, you wouldn't have a closed form. We cannot say that the cosine is equal to, say, x cubed or x. We just know the sine, and if we want to approximate it near the point x naught, we will need to know two things. First thing is we will need to know the value at that particular point, and we'll also need to know f prime of x naught. And we'll see in a wealth of examples how this plays out. So that's left for the next video.